Welcome to module 40 of Database Management Systems course in the IIT Madras online BSc program. In the last module, we took a quick look at different physical storage media options, particularly the secondary storage in terms of magnetic disk, which is going to be our mainstay of operations, and also the tertiary storages and other storage media as well as future. Now we are going to look at how to organize our database files in this storage media. So I should rather say that we'll start with the logical structures of the physical layer. How database files should be organized, how records in that should be put, what will be the data dictionary, and what would be the different fast access mechanisms. So for file organization, consider that a database has a hierarchical containment. A database is a collection of files. A file is a sequence of records. A record is a sequence of fields. Right? So this is the basic mental model we start with. This is how we will organize. So one approach that we can take, just to get started in simple terms, that we can assume that the records have fixed size. We can also assume that records are of only one type. We assume that different files are used for different relations. So every file is for a different relation. Every record is of one type only, and the size of the record is fixed. Of course, this is not in general will be true, but this is just to get started so that we can have a easy to implement formulation. Then we'll generalize to variable length records and so on. At this point, I would like to remind you that the database file is partitioned into fixed length storage units. We talked about this in terms of magnetic disk. We mentioned that while sector is a basic unit to write, blocks, a couple of sectors could build a block, which is the fixed length unit, which is in terms of which we do the storage allocation as well as data transfer. So a simple approach could be just to follow a linear array like structure. We say we store the records because each one of them is of same size. So we just keep them one after the other, and if we do that, then if n is the size of each record, then the ith record will be available starting from this address. So you know the offset, just like an array, and record access will get simple, but we have to make sure that records do not cross the block boundary. So if it crosses a block boundary, then some more computation will have to be done. Now in terms of deletions, what alternatives do we have? If we delete some record, suppose we are deleting this record, then what are the options? One is that you move, like the array, you move the rest of the records up, all of these records up is one option. Other could be that instead of moving this up, you take the last record and move it here. So you can move all of them up, just move the last record. Or a third could be that you don't move anything, but just mark that this particular record is no more in use, and that space is free, and chain them up as a free list. So these are the three basic strategies we can have. So if we do compaction, that is, if we remove the record 3 and then move the remaining records up, this is what we get. You can understand this is going to be expensive. Now if we do a movement, so what we are doing is we delete this and we move record 11 here. So, record 11 has come here, this ends in record 10. So, that is another option which may be good in many places. More common is using a free list. Store the address of the first deleted record in the file header. In the header of the file, you write the address of the record, first record that has been deleted. Use this record to store the address of the second record that is deleted. So, that is what? So, these are the free spaces. So, you are just chaining them up as if as a pointer. Actually, you do not need to have this separate pointer. What you can do, because you are chaining only the free spaces, right? They are not having the normal attribute value. So, you can use that space itself, a part of that space itself, as to mark that it is free and also put the pointer to the next free record, right. So, that way you do not put any space over it, but you can get, when you have to insert, you can check if you have a free space for a record and you can put your new record there. So, these are the three ways typically a fixed length record file can be managed. But in general, the records are variable length, right, because you may store multiple record types in the file. The record types allow fields, one or more fields, which are themselves variable in size, like varchar. You do not know how long it will be. Right? Some older record types allow repeating fields and so on. So, what is done is simple. The attributes are stored in order, like in the order in which you have defined. If you have a variable length attribute, you store it as a fixed size, like in here. So, what you say? You say you do not store the value here, rather you store an offset of where the value can be found later on, right. So, you say that it is 21.5. So, this value can be found here and its length will be 5. Similarly, the next value can be found at 26, which is Srinivasan, and its length is going to be 10. And you have these variable length fields after all fixed length attributes. So, kind of you have a fixed part, you do not have to really keep on searching as to where does this variable stuff end and what does my next attribute start. You do not have to do any of that. This fixed length part gives you everything. You know this order, you know what are each of the size. So, you can take any attribute directly, and if it is a variable length, you need to just traverse this pointer and get the actual value. And null values are represented by null value bitmap, right, as we are seeing here. Okay. Now, often what we do is we basically, because a block will have multiple records. So, it will be good to have what is called a slotted page, where the header contains a lot of information. What are the information? It says what are the number of record entries, how many records are there, where is the end of free space in the block, and the location and size of each record, right. So, it is like having a header information, a dictionary information for the records that you have, right. So, then the records can be moved around in the page to keep them contiguous, because nobody is referring to them directly. If somebody has to refer, he has to refer to the record in the entry in the header, not to the record directly. And of course, if you move the record around, you have to update the headers, but that is internal to the block. So, that way it becomes very efficient. Externally, you cannot see this rearrangement that you need because of insertion of new records, deletion of some records, or change of value for a variable length field and so on. Right? So this is slotted page with header is a usual structure followed. Okay, so that was about the basic organization of records in terms of the file. Now we will now see how they will actually be stored. Right? So we have seen the logical view. Now let us see how will they actually physically occur. So it could be a heap. A heap is, you just keep things anywhere and everywhere. Right? We talk about heap in the computer memory regularly for dynamic allocation. It could be sequential, where records are stored in sequential order based on the value of the search key of each record. Yeah, that's the tricky part. Based on the value of the search key of each record. Now, why are you doing this? Because if it is done in a sequential order based on that value, it can make you do something like a binary search more easily, and that's why you want the search key, the key basically. It could be based on hashing, where you use a separate function using some of the attributes of the record, and we will talk more about this. Or it could be multi-table also. For example, you might want to have multiple relations of your design in the same table. It's called multi-table clustering organization. It might minimize your I/O. So let's look at some of these. So this is a sequential organization. So what you do is it is suitable for applications that need sequential processing of the entire file. So you keep them one after the other, and these links basically tell you the order in terms of the search key. Right? So what will happen if you have to delete? All that you will need is to change this pointer link. Right? You will just skip that, put it to the next, and whatever got freed, you will put it to the free list. So pointer management, deletion is done. For doing the insertion, you will have to check if there is a free space from the free list. If there is free space, you put there. If it is not, then the block has run out of space. In that case, you may have to allocate another block, which is called the overflow block. And whatever you do, you have to now, it's like a insertion in the linked list. So you will have to basically insert this element using the pointer. So in this way, they may have too many of pointers going this way, that way. So periodically, you may need to do a reorganization and clean things up. Just make them more sequential. That's at a leisure time of the desk, you could do this reorganization. So that is a typical sequential organization. I'm not going to talk about the hashing organization, because as I said before, we will dedicate a separate module on it. Another is multi-table clustering. So just let us start with an example. So we have seen this relation number of times, the department, which has department name, building, budget, and which has also another table, instructor, ID, name, department name, salary, and so on. Right? So normally what you will expect? You will expect to keep them separate. Right? Now I do something interesting. What I do is I will group the records of instructor who are in the same department together. Right? If I do that, I don't need to remember this, I don't need to write this, because they are all from computer science. Right? So I will write a row for this department, as I write here, and then I will put the 3 who are from that department. So mind you, from this, the department name, from the instructor, the department name I don't need to keep. Then I put the next department, this is a department record, and I put the instructor who is working in that department. It's very different from the way you have logically designed. So what you are getting is, if you get a department, because what is the rationale behind this? The rationale is that there is a many-to-one relationship, right? Many instructor to one department. So there is a scope of lot of grouping, and since there is a many-to-one relationship, your expectation is there will be a lot of queries which will be done for a specific department. If that assumption is not correct, then this organization is not good. But often that will happen. If you assume, if that happens, then what is? Then all that you need is to come to the department, and then rest of it is available together. It becomes a lot more efficient in terms of access and processing. So multi-cluster, I mean, of course there are issues, because here the design is taken up in such a way that this has 3 attributes, this has 3 attributes, kind of it matches and so on. But there are different types, like on this there is a varchar computer science, whereas this may have been a number ID and so on. But we'll have to take care of those variables and variable types and variable size of records between the two relations. But conceptually, this is what can give you a lot of benefits, and often that is used that way. So it is good for involving queries which has department cross instructor, right? Because in department join instructor, because you will have to join department with instructor. So you have to go by the department, take all instructors, which is already done here, right? It is good for queries which have a single department and its instructors, right? So you can see that these we are putting together because they all work for that department, and then we are chaining the departments because it is done department wise. Again, this is possible because of the many-to-one property of the relationship. Now, it is certainly bad for queries which just have departments, because now they are not sequential, they have to go on the chain. This will obviously, as I said, will result in variable size records. Of course, we can add pointer chain to link records of a particular relation. There are different designs which do it in this way. So we saw the sequential. Heap does not have an organization, so I skipped. We saw the sequential, as well as we saw the multi-table clustering of multiple relations, and we will talk about hashing in the later module. The next that we have to look at is, I mentioned that there is, the database itself has lot of information to manage. What are the relations? What are the different attributes of every relation? What is the types of these attributes? What are the different views? What are the integrity constants? Who are the users? What is the kind of physical structure and strategies you are following, and so on and so forth. So database recursively uses itself by having a database called the data dictionary. It's often called the system catalog also, which stores the metadata. Metadata is data about data, because everything is a data and you are keeping data about that. So you are keeping data about relations, about attributes, about users, and so on. You keep that in a separate database design, and that is the data dictionary. So data dictionary has to be done very efficiently, because every time you have to do something, you have to go through the data dictionary to know where that relation is, or what is that type this relation is satisfying, and so on and so forth, right? So it may be that you want to make sure that the data dictionary, which is not expected to be very large, can always stay in the main memory and does not have to go back and forth with the disk, which will drastically reduce the performance. So if we just look at some typical examples, so there will be a table like relational metadata, which has relation name, number of attributes, what kind of storage organization you have opted for in this relation, where is the location where it can be found, and there is attributes metadata, which certainly talks about the relation name. So it is many to one, Many attributes can be there in a relation, but an attribute can be there in only one relation. Attribute name, its domain type, its position, because I said they will have to be in the specific order to be able to quickly, so that we can quickly locate it by offset. So the position is that kind of the offset, and the length. Position is I should say the ordinal number, where there is a first attribute, second attribute, seventh attribute, and so on, so that I can add all of those and get that number of where to find it, and the length. Right? We may have indexes on the relation. We have not yet talked about index. Index is the structure by which we can search on a relation very efficiently. We will discuss about index in the next week. But index, one or more indexes may be, 0 or more indexes may be created on a relational schema, relation. So it is again another many to one relationship, as you can see here. So index has a name, it has a relation for which it is an index. Index has different types, it has indexing attributes, and so on, right? So if we just look at even these three without any specific constraints or anything, it tells you a lot about how you have to manage your database's own data about the relations, indexes, attributes, and so on. There would obviously be a lot more. Then there are other tables like all the different views that you have defined, the user metadata, the user names, the encrypted password, group, permissions, authenticity, rights, and all of that would be there. Right? So all those that go into the data dictionary. Okay. So next we talk about the access of the storage. As we have said that the data is in secondary store, which is slow on the disk and so on, but huge. And the operations are data structures in the main memory, which has to be small, cannot be very large, but very fast to operate on. Our actual operations will happen in the memory data. So which means anything that I need to do, I have to bring the data from the secondary store, the disk, to the memory, operate, and put it back. Now, if I do it for every data item every time, then I will be spending all my time to just to read the data, write the data back, read the data, write the data back. First of all, reading the data from the disk itself is a much slower process than memory access, one. Second, there is a lot of network cost involved in transferring the data from the secondary disk, from the magnetic disk to the main memory. Right? So we have to minimize the requirement of such read and write transfers. Right? So that's a basic issue. So what we do is we have divided the storage in terms of blocks I mentioned earlier. So these are kind of units in which you will do the data transfer. Right? And what we try to minimize is the number of block transfers between the disk and the memory. So how we can minimize this? If we can keep more and more blocks in the main memory. Right? So for that, we allocate a area of the main memory to store copies of disk blocks, and that is called buffer. Once we do that, then the main issue turns out to be how we manage this buffer. Buffer management becomes a big question. So we have a buffer manager, a subsystem responsible for allocating the buffer space in main memory and managing it. Right? So let's look at some of the basic issues that are involved. What will happen with a buffer manager? So the program calls on the buffer manager saying that I need a block from the disk. Right? Send a block from the disk. Disk has a block has an ID and all that, he says that. So what are the possibilities? One is the block may already be there in the buffer. It was brought earlier by the program. So it may be already there in the buffer. Then the buffer manager will simply return that address to the program that this is where your buffer is, just one block. The other possibility is the block is not there in the buffer. If it is not there in the buffer, it has to be brought from the disk to the memory. If it has to be brought from the disk to the memory, then I need space in the buffer to put it. Now, if the buffer already has space, I will be able to bring the block and keep it there. If not, then you have to replace or throw out some existing block, because it is a limited space, and then by that process make space. Right? Now, whatever you throw out already have updated data. So, whatever you are replacing may need to be written back to the disk if it was modified. From the last time it was written back or last time it was fetched. Now, if it was not modified after that, you do not need to write back, you can just use that space. The disk already has an identical copy, but if it was modified, you have to write back. So, with this process, the allocation gets completed. Once the allocation gets completed, you read the block from the disk to the buffer and return the address. These are the basic, logical steps involved in the management of the buffer, which sits between the program and the disk, to make sure that the program will always get its block in the buffer. Now, certainly, when you decide to replace, the question is, the buffer has multiple blocks, which one would you replace? If you have studied operating system, I am not sure if you have, then you have come across this issue of page replacement policies and so on. So, it is basically very similar, though I should say the consideration factors may be different in this case, but the strategy is just similar. So, WAIS has one strong strategy known as LRU, least recently used. What is least recently used is a block which in terms of use is the oldest. It may not be oldest in terms of fetch, but in terms of use it is the oldest. So, if it has not been used for the longest period of time, then you expect that, well, the program is no more interested in it. So, you can use that space. So, the past pattern of references is a predictor of the future reference. That's a basic idea. Now, queries often have well defined access pattern, such as it may have a sequential scan, and the database system can use that information to predict future references. This is something which often is different from the kind of challenge that an operating system has, where the predictions are a different ballgame, but here it often follows a certain query structure. And LRU may be a bad strategy for certain access patterns. For example, you are doing joins, so you have nested loops. If you have nested loops, then you are going to repeatedly use in the inner, when you are working in the inner loop, you are going to repeatedly use the outer loop stuff again in the next iteration. So, if that turns out to be your LRU, which it might, then you are replacing and bringing back the same block multiple times. So, I am just talking about giving you pointers to what could be the different considerations which might lead to a mixed strategy on the replacement policy that you are going to use, and often that comes from the query optimizer. So, some of the policies involved, one is pinned block. Pinned block is one you can pin a block. So, say that this memory block cannot be written back. So, you can do a toss immediate strategy, where the space occupied by the block is considered free as soon as the block has been processed. It can then have a most recently used strategy, that is a system pins, that is you cannot replace the block currently being processed, and after the final tuple of the block has been processed, it is unpinned. So, it becomes a most recently used block. Right? So, buffer manager in general can use several statistical information regarding the probability and keep the data dictionary blocks mostly in the main memory, its own data dictionary. That's a heuristic, as I was saying, that data dictionary you are going to use every time, right? So, what's the point, bringing it every time? You should have a separate allocated space in the buffer where you just keep it in the memory. Right? So, these are it can also support forced output of blocks for the purpose of recovery, that you write back because you need to do a recovery and so on. So, there are the different buffer replacement policies that this goes on to make sure that you have a better and better performance. Okay, so with that we come to the end of this module. We have given a fair idea about the organization of typical database files, how the records are laid out in that, what is the importance of data dictionary storage, and some of the storage access mechanism, particularly the buffers and buffer management strategies. Thank you very much for your attention. Going forward in the next week, we will start talking about indexing, and you will see the impact of these design considerations on indexing and how to make, what are the different ways to make accesses more and more fast.